So thank you everybody for coming. We'll share some results that we've gotten. We actually have a fairly substantial portfolio of work of using AI in the development process, trying to both understand how it can be used to improve productivity, how well it works, as importantly, where it doesn't work. This particular piece of work that I'm going to be sharing today was done with a team, and I want to acknowledge the various folks that we had working on it, people who helped perform the experiments, did the data analysis, provided some of the interpretation. So we actually drew on a lot of expertise in order to do this. I'm going to give a brief, very brief introduction on generative AI. By this point in time, as I said, this is the ongoing work we've done, but I think many people are familiar with the key tenets of generative AI. And then we're going to set some expectations that we have seen other people set. And part of the challenge in this area is that expectations may not meet reality. And so we'll go through some initial evaluations that have been done and share with you our experiments and then some of the implications of those experiments, where it might go next. So everyone's familiar with autocomplete. You take your phone, type in a couple of words, it comes up then with the next word. This is just done by a statistical analysis of what typically comes next. And on a phone and these kinds of systems, it's a modest amount of data that's looked at in order to figure out, given a couple of words, what the next word might be. What has changed dramatically is that instead of a couple of words, we now are looking for thousands of inputs. Tokens is a generic word for it, but think of it in words. And then what should be the next following 1,000 words that should come out? And when you do something like that, the qualitative results are really quite astounding. So now, if you talk about autocomplete, and in a very crude sense, that's really all we've got here, is I take 10 words or so, and what would be the next logical 100 words that would come out? Well, you see all sorts of things that came. I personally don't know whether that is a good sonnet or a bad sonnet, but just to illustrate that it's not just the one or two words that autocomplete gives you. Now, this is actually not new within the software development environment, just like it's not new on your phone. In software development, this idea of autocompletion using the same kind of analysis has been around for a while. So this is a slide from a talk I gave back in 2019, where I was saying, look how you can use this kind of AI technology in order to predict the next line of code that should be written. And you can see from the snapshot there, I was making the guesses of what might come next and probabilities of what kinds of things you'd like to use. For those who may not notice some of the details there, the actual technology used is generative pre-trained transformer technology, otherwise known as GPT. So when you see about GPT 4 or 5 or what have you, note that GPT 2 was being used for autocomplete in program development 7 years ago. But what does that look like now? So again, we start with a modest description and pow, all of a sudden you get pages and pages of code. This is a pretty remarkable kind of thing to have witnessed. When you see that, though, you start getting people's reactions like this. It just got done debugging my code. Here's how you use it to write code. It changes how I write code. It's revolutionary in how it writes code. It's the solution everyone in development has been looking for because everyone knows that software is always late, not on spec. Well, you expect the trade press to do hyper kinds of things. And so most people who are discriminating will see that and say, sure, we understand what's going on in the trade press. Silicon Valley is somehow enthusiastic as well. You see people like Mark Zuckerberg over in Meta saying that he's going to start automating the work of mid-level software engineers this year, and it may eventually replace all the coding on its apps. And you see people like Mark Benioff at Salesforce saying that, well, we're going to have less engineers because we just can use this instead. So, there's a lot of people who are making a lot of predictions about how this might work. What I found a little more scary, however, was Wall Street. We have people like the CEO and director of BP Oil saying that he doesn't need so many coders. And you have Alphabet and Google saying that they're generating all this new code and then it'll be accepted. Now, the reason why I use the phrase that it's scary is because one thing for the trade press to do hype. And Silicon Valley, is selling their own goods, so you kind of expect them to also overstate this. But CEOs telling Wall Street what's happening is kind of dangerous thing because if it doesn't happen, Wall Street punishes them in their stock price, and most of these folks make a lot of their money from their stock options. So this is a more serious kind of prediction that's going on with sort of more practical ramifications, at least for collections of folks. Now, of course, there's a lot of tool vendors out there who are doing this, and they're a little more cautious when they start to see how this might work into their tools. And so they've done a variety of tests and models, and they've noticed that, well, it generates insecure code. In fact, one study by Veracode that almost half the time it introduced a security flaw. Each of these had their own particular quirks as to what they were looking at, which kind of flaws they were looking at, what kind of language they were looking at, and so on. But the point was that when they started doing some more systematic measurements, it didn't quite match the hype that you've been seeing. And that's sort of true with what I call the academic research as well. The upper left is probably one of the most commonly quoted ones that came out of Stanford, in where they looked and said, they wrote less secure code when they had access to these kinds of things. You see other work here done at NYU and at Princeton and Chicago. Um, uh, that there's just lots of times when they built these things. University College London, it can only figure out what went wrong less than half the time. And as a result, the more systematic the studies became, the less well-performing these things seem to work. Now, a lot of these were sort of classroom exercise kinds of things. At Stanford, they had, write a simple application that does a database lookup. Um, in the UCL version, they use what I call computer science kinds of programs. It's like find the greatest common denominator. It's a typical kind of thing that you might ask a computer science undergraduate to write, but how realistic is that as far as it goes? So we thought we might be able to do a bit better. And we did that because we had built something called the Secure Coding Standards. We have done code evaluation for well over a decade, almost getting on to 15 years or so. And without exaggeration, have evaluated over 100 million lines of code, looking for problems in them and providing reports to people who have given us that. And as a result, we have got a lot of experience about what works and what doesn't work. And we've built these standards. We've encoded that knowledge in these standards. And relative to the particular task at hand, the standards have a particular organization. So for each standard that we provide, each rule that we claim, we provide an actual example of how that rule got violated. That's sort of in this pink box. In addition, we always provided the way that it should have been written. So you see the correct answer, if you like, down in the blue box. So we have hundreds of these rules where we have the examples of what went wrong and how it looked and how it went bad. So we could actually feed the bad examples into the system and compare the output to see if it got the correct answer or something close to the right answer, because obviously it's not necessarily a single answer. And that's where some of the SMEs that I referred to earlier in the talk helped. Now, my intention is not that you're experts in C or Java or C++ or any of the examples we're going to give. I don't really intend for you to study the various code examples that I'm going to put up at various times. I'll explain what I hope is the relevant information. But I also know there's going to be some people who insist on looking at it. So just for your information, if you wanted to know what this particular one was, it was using the wrong formatting string in a print statement in C. So there's the mistake, there's the correction. And again, my goal here is not to teach you C. So what is it that we actually did? So we took approximately 1,200 examples of these rules or various standards. And as you can tell, this is sort of ongoing research, and the research continues to go in various directions. But starting back in 2023, we looked at Chat 3.5, we looked at Chat 4, GitHub Copilot, Chat GPT 4.0. We did thousands of runs. We decided not to do any repeats. And the idea was we didn't want the system learning from what we had given it. And there are some ways that are supposed to prevent that, but we wanted to be as clean as we could. Full disclosure, all of our standards are on the web, including the bad answers and the right answers. And so everything there, along with our solutions, were available according to the time frame that OpenAI claims that ChatGPT was trained. So if in fact it walked the entire internet, as they claim they do, or the open internet, it has seen everything that we've already about to give it already. And in some cases, the examples even have comments saying, look, here's an error on the next line. And to the extent it can find those kinds of things, that would help it find what's going on. Every now and then, as I said, the answers it produced weren't obviously a wrong answer and weren't the exact answer that was part of the standard. And so we use SMEs to evaluate whether the result that came back actually was still legitimate or not. And some of the details of those experiments are written up in the references that are at the bottom there. For the most part, and I think if you didn't notice it, you can go back and look at it later. For all of these pieces of information, we provide references on the slides if you want to go back and look at the original material. So just looking at some examples, this was, in fact, the one that we just started with, the wrong character string, formatting string. And in this case, 3.5, 4, and Copilot all found the error. By the way, when I say Copilot, I always mean GitHub Copilot. Microsoft has used Copilot as sort of a marketing term for lots of different things. I literally mean the one that's in GitHub and used as part of GitHub, and I'm just not going to qualify it every single time that I do that. So just heads up. Now, it also changed as it went from 3.5 was sort of an initial version, and both 4 and Copilot are derivatives, further evaluations of them. And so one of the questions was, well, how did that change? Well, 3.5 gave you the error and kind of gave you a description of the error. As you see here, the format was wrong, and you should use different formatting strings, is what that says. Okay, so tells a programmer they should go and make a change. What we saw in the other systems in 4.0 and Copilot is not only did it describe what was wrong, but it also gave you the new error. And so, sorry, it gave you the corrected statement. And so it helped the programmer not just understand, but also provide the answer, which in some circumstances is really what they're looking for, in order to cut and paste the correct answer in there. So you see that it's a lot more verbose because it has a more extensive description and it actually is providing some corrected code. And so as it turns out, so just in aggregate, we found that 3.5, we took all the outputs we have and just kind of smashed it together, is about 400 pages or so. You got 50% more with ChatGPT 4, and you got a bit more with Copilot. So you definitely got a lot more chatty output from this. So one of the things we saw as the systems evolved is they started providing a lot more description and answers to the questions. Now, I gave an example where it got all the right answers. Doesn't always get all the right answers. So again, my point was not to teach you C, so I'm not going to bother putting out the C code of what it means to have a flexible array member. But 3.5 said there's nothing wrong with this code. 4 said it's an appropriate use of the code. Copilot said seems to be correct. So it basically missed it entirely. In other cases, the more advanced systems, the ones that came after 3.5, did better. So for example, this is, don't read uninitialized memory, uninitialized variables. Again, the details of the code are not that important, but in 3.5, it says there's no obvious errors here. In 4 and Copilot, it says, oh, we definitely see an error. There's an uninitialized variable. In one case, and it sees an error is not initialized. So it did get a little bit better, and we'll explore a little bit more about how much better these things got over time and what the future might happen here. Now we saw some other things that are kind of common with AI systems in general. One is memorization, reflecting code back. Here's an example where we gave it the right code. So far, I've been giving you examples of code snippets that had problems and couldn't find it. This time we gave it the correct code and said, can you find anything wrong with here? Presumably you shouldn't. And it invented something. The password should be hashed directly from the character string without converting it. Well, that's not a problem, actually. And by the way, it was done correctly in the compliant code, and in the results that came back, it spit the whole thing back at us. So basically memorized what came in and spit it back out and didn't realize that there wasn't any problem to begin with. By the way, this is 3.5. The later versions had the same behavior. That this particular error, which was not demonstrated in the example we gave, but SQL injection attack, and this one has no SQL injection vulnerability in it in the correct code, but it still complained, and it didn't get any better here. Now, initially, we also saw something that we thought was really kind of interesting. Again, not intending for you to read the code, but what it is it's sort of simulating a banking transaction and where you have two people trying to change an account at the same time. Classical race condition where you might have one person stepping on top of the other as they're doing it. And when we gave it to the system, it came back and said, "Oh, looks like you got a race condition here." And then it gave a little bit of explanation about what that is and how one should write code in order to get rid of that particular problem, which we thought was really quite impressive. I mean, that's sort of not just a generic code completion kind of thing, in where you might say, "What comes next?" This is more of a complicated kind of analysis. And we said, "Gee, this really strikes us as impressive." And then we got to start thinking, well, how much of that is really going on? So we fed in the correct program, the one that had no errors with it. And guess what? It came out with the same problem. It said, by the way, it looks like you've got a potential deadlock here. So we started thinking, well, maybe what's going on is that we got some kind of pattern matching. If it sees calls in the language in the program that talk about locks and mutexes and things of that sort, it always says, well, whenever I see this, the context is there's probably kind of deadlock stuff going on. So just spit that out. Sometimes it can be hard to figure out whether you got the right answer or not coming out of the AI system. So I'm not going to spend a lot of time on the code here other than to say on the key element here is that there is a composite type, a structure, in this case, a character, an integer, and an array of bytes. And the error here is that you comparing all the bits in memory for the entire structure. And the reason why that's not a correct thing to do is because compilers put in additional space, or they could put in additional space between pieces of the structure. And if you start comparing them bit by bit, you're going to wind up comparing garbage and therefore not get the right answer. The right way to do it is you should be comparing it field by field in the structure. So instead of doing a mem comparison, which is what the top one is, what the left side was, you actually compare it right on the right side, bit by bit. And again, the actual array of bytes is now contiguous, and so there it is appropriate to use the memory compare. So that was a place where, because it was just an array of bytes, that was okay to actually dive right into the memory, not actually iterate through each element of the buffer. So what happened when we fed it into the system? So 3.5, it actually came up with the right answer. It said, hey, you're using memory compare for a structure. You shouldn't do that. It's because it's comparing things that are got spaces in the structure that could cause memory to fail, the memory compare call to fail. Now, the way it suggests fixing it, if you look real carefully, is it again does piece by piece. First it does the left, then it does the right, or sorry, it does the character, then it does the integer. But then for the array of bytes, it says you should use a string compare. The problem is this is an array of bytes. This is not a string. And so it's actually giving a different answer than we showed before. The question is this the right answer or not? Now, purists might say, in an abstract sense, in C, there's no way to tell by looking at that structure, looking at that array, whether it's intended to be used as a string or intended to be used as an array of an array of bytes. Now, it turns out there is a variety of research in this area already in reverse engineering that says and for those who are not familiar with reverse engineering, you take the binary and try to reconstruct the source code from it. And from that, they've deduced that if you look at certain kinds of patterns, you can deduce how things are intended to be used. So, for example, if you look at a C program and you see what looks like this array of bytes, if you have names, if you have identifiers like a name, address, uh, um, uh, the size, what have you, those are almost always strings. If you have things like buffer, that's always arrays of bytes. And so if you had done analysis of lots of C programs, you would see that something called buffer is almost certainly to be a collection of bytes, not a collection of characters, and therefore it actually should have used the mem compare, not the string compare. And those will give you different answers for different situations. By the way, it turned out that the later versions like Copilot, actually got this right, and they figured out that that array was actually an array of bytes and not a string. So again, the AI research has already figured out that this can be done, and 3.5 couldn't figure that out. Later ones actually got better at it. By the way, it used the wrong string comparison, even if you're going to do a string comparison. Now, here was another kind of interesting situation. Um, for those who are not familiar, this is the generalization of SQL injection. It's command injection. It's a very, very bad thing. You don't want to do that. It causes can cause very bad things in your program. 3.5 didn't catch it at all. Instead, it came up with some kind of thought that somehow the string printing function was wrong. It says to use a different one, although the one it suggests to use is already there. So its suggestion made no sense even from that context. But it missed the real error, which was the use of command injection or the potential for command injection. Now, the later systems got it better. ChatGPT 4, was really quite explicit about this. Danger, danger, Will Robinson. This is a command injection security vulnerability, critical issue. Don't do this. Very good. Very thing you should do. When we went to Copilot, we got this response. So, sometimes you can't always get what you want. By the way, we actually pushed Copilot a couple of times. This is one of the few cases where we actually did repeat the exercise. I said at the very beginning we didn't because we didn't want it to learn. Here we kept pushing, and eventually it came out and said, here's how you use this vulnerability to delete all the files on the computer. So we didn't put any of that code into the presentation. So what do we have seen with large language models? Well, sometimes they get it right. Sometimes they get it wrong. They seem to improve to a point. We send memorization, both memorize the correct code, memorize bad code. We see inconsistent pattern matching. We sometimes see subtle mistakes in the fixes, and we'll talk a little bit more about that later. We see hallucination of inventing non-existent problems, and sometimes you'll see problematic guardrails, things that you think you ought to get answers and you don't. So, it is a tool, but it's not a panacea. Now, and several times we said that it got better. So just again, we have all the data in those various articles I shared up front, but just to give you a summary version of how well it did between 3.5 and what I call 4. And 4 includes 4.0 and Copilot, just for sake of brevity. And you see that it does improve over time from 40 to 60% in some cases, up as high as 80-ish% in some of these other examples. And this is looking at both correct code and incorrect code and whether it got it right or not. Now, I've been exchanging information with other folks who work in this field, and we have a concern that this may have plateaued. And we'll talk a little bit about more later with some of the other results we see. And that's because these systems work by ingesting a lot of data. They've already ingested all of GitHub. They've already ingested the large public repositories of information. What more information are they going to get that will improve the models? And the answer is we're not sure there's that much more information to get. Now, agentic AI and all sorts of other kinds of augmentation techniques that might be applied, we think is how they'll get better. But just as raw large language models, this may be as good as it can get. But as a result, in order to use these systems, you've really got to be an expert. If you're not a great coder, this is from the person at Price Waterhouse who has folks doing this, you're not going to see when something goes wrong. Another engineer out of Facebook says that when things make mistakes, it takes a really experienced developer to be able to spot them and know how to fix them. However, when you actually see how people behave when they're given these systems, and I think this is generically true about AI systems, they tend to defer to the AI systems over their own judgment. So in one case, this again goes back to the Stanford study, the people with the AI assistant were most likely to believe that they got secure code from the AI system. That when they talked about did their own investigations, they strongly believe the AI the AI suggestions. They did check mark when they did out their surveys. They found that AI is not only writing the code, and deployers are just hitting deploy. They just use this code. So it's kind of scary as to how well this stuff will actually be deployed in practice. So how can you do better? Well, context is the key, being able to control the narrative of how you interact with these systems. I think that's generically true for large language models in general, but certainly it's true in programming. So let's just take one simple example. And again, this one's kind of a funky example. This is again the UCL study where they did what I call the computer science programs. And they gave an example up on its own. It did 19. If they said, oh, try this other thing, it could figure out maybe 41 times, 31 out of the 41 bugs. But for example, one of the prompts they gave it was the greatest common denominator. Oh, here's an example, and you got the wrong answer here. Well, when you did that, it got a little bit better. Now, there have been some more systematic studies here. And this is a whole collection of things. And in these papers, they have lots and lots of data and lots of analysis and charts. And I've summarized them down to, I hope, something consumable in a talk. But they tried different levels of prompts. So if they just said, go fix it, it got it right 20% of the time or so, 30%. If they said, generate the fix for this particular error, CWE is a conventional way to denote a particular class of errors. If you don't know what those are and you want to know, I can tell you all about CWEs offline. And then it got up to almost 40%. If you actually gave it the error message that came out of a static analysis tool, like Coverity or Fortify, it could get up to 60%. If you get some more context of the error, that here's the CWE, here's the actual alert, and go take a look at this loop. It can get up to 90%. So by really focusing its attention, no pun intended. However, if you got real details saying, change the incremental value of I in the loop, all of a sudden it got worse. I don't have an explanation. The authors don't have an explanation, but it was in the data, so I'm sharing that. Now, they examined a different set of programs, and unfortunately, I could not abstract this very well. If they said no prompt, then they were able to fix things 70% of the time. When I say extensive prompt, they would say things like, and assume you're using this library and it's this language, and these are the kinds of things that happen, and this is kind of how the output should be. It really, a complete analysis of the context of the program. And when they did that, they got, almost 97% of the time they could get it fixed. Uh, those first four on top are relatively repeatable. You can look at those and figure out whether you do them yourselves. On this last one, there was a lot of creativity in the prompts that they generated. And so it's an interesting study, but I don't know how easy it is to reproduce. Now, there was another interesting event. Amazon wanted to upgrade their Java 8 and 11 programs to Java 17. They went through an interesting approach and they claimed that they saved 45,000 developer years in doing this. How did they do that? Well, they used their own LLM, specifically trained on Java 8 and 11 to Java 17 upgrade. So they trained it to look at those kinds of examples. In addition, because it was corporate programs, the inputs, the things to be changed, were not the whole gamut of what programs look like, but they're programs written to Amazon standards. So they had pretty standard patterns to go match. In addition, they trained it on something called the open rewrite recipes. There's things written down in the literature about how this upgrade should be done. And so they trained it on what an upgrade should look like. What I think was sort of most important is that they reused existing tests. These are already existing programs. They had unit tests to see whether they worked or not. So after the change was done, they reran those tests in order to see whether the new one was still correct or not. And sometimes it wasn't correct, and they then go fix it. But they took the human basically out of the loop. Before, the systems would generate the corrected code or different code, and it was up to the humans to sort of stare at it and say, yes, I believe this, or no, I don't believe this. That had a lot of errors, a lot of deferral to the AI. Here, there was an objective way to measure whether the output was what you wanted or not. Does that mean now everybody should start to go do this? Well, there's a study done at MIT in where they said, well, can people really build their own systems like this? And it builds. They fail very often, and only 5% of the tools that they actually built actually was able to be used. So if you've got all those skills that Amazon had, going to do the investment, had a really controlled environment, it might work. But in general, that might be a very risky approach. So what does work? Well, here's an example of some of the research that we have been doing and others as well. My goal here is to try to limit or control how the human involvement is. So in this particular line of research, and again, if you want more, there are references there, is you run the program through your favorite static analyzer that puts out a bunch of results. You feed those results into the large language model along with the program and say, okay, how do you go about fixing this? And more importantly, you can ask these systems, how do you know that's how you can fix it? And so it spits out the right answer, presumably, and it spits out the explanation of why that should work. You feed that explanation, and again, you ask for it in a formalism. You feed that into some sort of theorem prover. Now, the theorem prover then takes the new code, takes the proof, at least the assertions of the proof, and actually verifies whether it met all the criteria that it was supposed to meet. So again, you took the human evaluator out of the loop for the most part and referred it to the theorem prover. And yes, in general, I'll trust my theorem prover as much as I'll trust any kind of automated system like a compiler or what have you. And so we get the somewhat judgmental human in a very modest role here. So this is in general how one might try to improve code that you've already got. But I want to go back and revisit some of the claims that were made earlier. So I showed you about autocomplete and being able to generate code. And I said, gee, that looks great. And most people looked at it and looked great. If you inspect it a little closer, you'll find out that it actually didn't write the code. It wrote all the boilerplate. And then the hard part is said, here is where the actual work should be done. It didn't deliver the actual work to be done, which is a little distressing because guess what? This particular work has been documented over and over again. Over 1,000 years ago, this was documented over in Spain. Gauss did it again in Germany. By the way, the Jewish Easter is how they used to call Passover back then. And so, it presumably had access to all of this, but was not able to do that. Instead, you saw sort of this, insert the right answer in the middle somewhere. So, it's not all that creative, but it does have another value. So I did the same exercise with Python. I could program Python. I know Python. I did not know that there was a built-in function to do this in Python. And so I said, give me a Python program to do this. And it says, hey, there's already a function to go do it. And here it is. So again, using these large language models, not necessarily for just find the errors and see, but in order to improve your productivity, I was able to learn more about how this might be accomplished in a way that I did not know. And so in some cases, it can work. Again, the MIT study, when they looked at it, when you saw things that were repetitive, simple, general, it worked. And so again, it has a place. It's just not a panacea. And I think the industry is evolving its thinking here as well. So remember back in the beginning, I showed that Mark Zuckerberg said, we're not going to have mid-level software engineers and maybe all coding by automation. By August or so, it kind of shifted and said, well, we're not going to replace them. Now we want programmers who know how to use AI as part of our process of hiring new people. Because as I mentioned, there are places where you can use AI that makes a lot of sense that do help. And they eventually got to the point where they are now, where they're saying, hey, this stuff is good. We want all of our programmers to use this as part of what they're building. And so it sort of evolved from we're going to replace you all to let's see if you have some skills to, gee, this ought to be just the skill that everybody has. And so when you read articles about you're going to have massive layoffs because AI is going to take it over, there actually isn't a whole lot of consensus here, but you do see a lot of productivity improvements. And as a result, learning AI by developers is probably going to be a requirement going into the future. And in particular, what have we seen? We see assistance. It autocompletes common patterns. That's pretty old news, as I've shown you from years ago. It can generate the skeleton code, not necessarily the real creative code. It can help look for documentation for capabilities. It can assist with repetitive tasks. Other people have been using it for generating test cases, for writing documentation. So there's a lot of ways it can be used. It's just not the replacement for a programmer. And as a result, there is value here, and it's all about setting the right expectations. So, it's one of the slides that I actually use, at people get so enamored with these kinds of systems, look at all the great things they can do. It's not all the things that you can do with a real programmer. So what would I like you to walk away with from sort of this discussion? Well, don't exist, don't no, don't abandon what you know now. Everything that you've spent time learning, tools that you're building, they still remain valuable. As necessary, educate management development on sort of what I call reality, separating the hype from capability. Again, you see, especially if all they do is read the trade press, you get those kinds of conclusions. There's a lot of what I call low-hanging fruit. We mentioned some of them like auto-completion and documentation serving, snippets, and so forth. That actually produces productivity. The various folks I've talked to, and it seems to match some of the statements that remain in the press by some of the larger development organizations like Google, between 20 and 30% improvement in function in productivity. Because it takes a long time to actually go find something in documentation that may not exist, or that may or may not exist. And for the most part, the correctness and manifest of these small snippets are available. And if you guide it, like I mentioned earlier, it gets even better. If you're in one of these special situations like Facebook found them in, sorry, Amazon found them in, you've got a extremely defined target and context, and you've really got the talent to go do this. And you have a way to evaluate the output to make sure that that you're not being fooled because you're not relying on human judgment. Then you might really have some spectacular gains. So I just thought, again, share some of the experiences we've had. We continue to do research in this area. There's a whole variety of different things that are going on. And I appreciate the time that you spent with us.